I think you already saw this slide. And looking at what we talked about with Hank, we know that evolution is when you change a distribution. There are 3 different ways that natural selection, which is the mechanism of evolution. Okay, so that's the basic. We got 3 ways that natural selection can change a distribution. We're going to look at stabilizing selection first. Okay, in stabilizing selection, being average is a great thing. The average is selected for, it's favored. We talk a lot in evolutionary biology about selected for and selected against. Selected for means it's a good fit for the environment. It works. It becomes more common. Selected against means it's a bad fit, and it becomes less common. So if we look at a distribution where stabilizing selection is occurring, we have that bell curve, that normal distribution before, and if that average is being selected for, especially really intensely, that normal curve is actually going to get skinnier and taller. So being average works for you. Being at either extreme is a bad thing. Extremes, we would say, are selected against. They're not a good fit for the environmental conditions. And the mode is the same as the mean, and the mode is being selected for. So the most common measurement. And again, because we're just talking about a single trait here, we can talk about this for any trait we can measure. Height, leg length, tail length. If we had a graph that showed fur color based on a continuum, we could do it for fur color. Any trait that we can measure, we can look at the distribution. We can look at it before some environmental change and after some environmental change, or after some number of generations, and we can figure out what kind of selection we're seeing. So this is where we can, in disruptive selection, is where we can see a normal distribution become a bimodal distribution. Because the extremes are the better fit for the environment. They're selected for. An average is selected against. And this is a really powerful path to forming new species, as you might imagine. Differences are being enhanced, and so the population is getting more and more disalike. We're losing our middle. Okay, this is the last kind of selection of the 3 modes of selection, directional selection. It's pushing a species in a particular direction. So values at one extreme are selected for, either larger than average, darker than average, smaller than average, lighter than average. And what happens is that hump in the bell curve, the mode, moves in one direction. It doesn't split, but it moves in one direction. And what you see is that one extreme is selected for, one extreme is selected against. After enough generations, you still can end up with a normal distribution, but it's going to have a higher or lower mode than the old distribution. So, how fast do you think this happens? How fast do you think evolution can happen? First of all, whenever we ask a question like that, we have to define some terms. So when we say evolution, are we just talking about any biological change over time? The one explained or stated clearly video said, in one generation, evolution has occurred. There has been a change in heritable characteristics. You had the different little wolverine with furry ears and long claws in a different combination. I'd say that's sketchy. Because really what we're talking about when we talk about evolution is a change in frequency of traits in a population. So how long before we can observe a change in frequency in traits? Can it happen in a single generation or in 2 generations? Does it take billions of years for there to be a shift in frequency of traits? How long did they say it took the pepper? Do you remember the peppered moths? Oops, wasn't recording. Okay, so when we think about the peppered moths, that might have taken 10 generations. It might have taken a year. We talked a little bit about how you're taller than humans were a couple thousand years ago. And I was just, where were we? We were just in a museum where there was a suit of armor. Oh, we were at the Art Museum in Pittsburgh over break. And I got to walk up to a suit of armor, and I was like, I'm pretty tall. Because I am, compared to a medieval knight, and this is a big warrior guy, and I was kind of looking down at the eye visor. Giant. No, I'm not. I'm average. But average 600 years ago was different. So is that evolution? It's a shift in the distribution of a trait. Height in humans. Yeah, that's evolution. How long did that take? A couple hundred generations. Could we see an observable difference in it in 100 generations, in 10 generations? Yeah, we could. So if we're going to talk about development of a new species, which is really what we think about when we think about evolution, so we said, how long does it take? Well, we have to know what we're talking about when we talk about evolution. If we want to talk about the development of a new species, the question we have to answer first is, what's a species? So how many of you have ever considered what's a species? Let's talk about that. I want you to take one minute. I will give you literally 60 seconds from the time I say go. Hold. Nope, wait, nope, no questions. Not yet. I'm going to give you 60 seconds from the time I say go. You can go join a table. Discuss with whoever is sitting at your table what makes a species. How do we define it? Go. Okay, so what you guys have is, pretty much you all came down to something to do with their traits, their characteristics. And it seems like you're all talking about physical characteristics, how they look, maybe whether or not they have fur, if they have a tail or not. And we looked at it from both angles of traits that separate species versus traits that species would share. So if you're in the same species, you share traits. We're all humans. We all have 2 eyes, 1 nose, 1 mouth. We all have a belly button because we were connected via an umbilical cord to somebody. Basics like that, okay. So what does biology say a species is? You knew we'd get to that. Interestingly enough, there have been 2 different definitions of species over time. And the first one is what you guys are all going for. So this is morphological. This is the morphological definition of species. Remember, morph means shape or form. So this is the definition that's about how something is shaped or formed, how it looks. And we define a species by their appearances, internal appearances and external appearances. So we can dissect 2 creatures. And if they have the same organs, oh, yep, they both have 3-chambered heart, they both have a liver, they both have a pancreas. Turkeys and chickens are a great example. Turkeys and chickens actually have some internal differences. If you've ever butchered turkeys and chickens, I don't remember who has the double pouch. It's turkeys, I think, have this sort of like 2-pronged blind pouch coming off the intestine that chickens don't have. They're pretty similar. They look a lot alike, but there are some subtle differences. So that was the oldest definition of species, is morphological. These things look alike. They're the same species. The big difference is variation. That you can have 2 members of the same species that look very, very different. And we looked at cases of extreme variation in humans. The 6-foot 3-inch blonde Danish supermodel and the 4-foot 2-inch African Tutsi, who's very dark-skinned, very short. She's very light-skinned, very tall. They're the same species. They can have a baby together. That's what gets us to our next definition. So the biological definition of species was the next definition that came about. So these are both older definitions. Neither of these is totally the modern definition. So the biological definition of species was, if they can interbreed and they can have fertile offspring, they are a species. Easy enough. They can have a baby and their baby can have a baby. They're the same species, no matter how different they are. There are problems with determining whether 2 things are the same species then if they're extinct. We can't take two dinosaurs and mate them. Can't be done. We don't have them on hand. There are also species that reproduce asexually, and that's a problem. You know, they don't partner with something else to mate. So how do we determine if they're a species? So we have a more modern definition of species that gets past both of these problems. So the modern definition of species incorporates both the old morphological definition and the old biological definition, but we add the modern twist of DNA. Obviously, we now know about DNA. We have the ability to look at DNA. It's the logical thing. So the modern definition of species includes the fact that they share physical traits, which is where all of you went. They also have to be able to produce fertile offspring. And we also tend to look at how much DNA they share. Like we talk about the amount of difference in DNA between any two humans being, what is it, like 0.001% difference between the Danish supermodel and, you know, the African Hutu. So tiny little variation, tiny little bits of difference in DNA can make a big difference in physical appearance. So what we look at is, you know, do they share a bunch of genes in common? They have some structural similarities. Can they produce fertile offspring? So if they are two things and they are the same species, they're going to look similar. They're going to be able to produce fertile offspring, and they will have some genes that, you know, we say, well, if it is a Acer saccharum, sugar maple. If it's a sugar maple tree, it has these genes in these locations. So we can look at DNA from a bunch of maple trees and determine if they're the same species. So if we look at things that are not a species, maybe they look really, really different and nobody would ever mistake them for being a species. A crow and a chicken. Nobody's going to look at a crow and a chicken and say, aha, I think they're the same species. They're clearly not. There's way too much variation there. And a crow and a chicken probably could not even produce offspring, let alone getting to the fertile issue. Do you know of anything that produces offspring, but then the offspring isn't fertile? I asked about my anglers for a reason. I mean, you can't do DNA analysis at home. But, well, we've got a few examples of those non-fertile hybrids. So you can have a non-fertile hybrid where two species that are related to one another produce offspring, but then the offspring are not fertile. Have you heard of this? Anybody know what that is in the pictures in the top? This is a donkey. Meow, meow. I do a terrible donkey. You know what that is. It's a horse. They're big, they're graceful, they're pretty. Everybody loves horses. Nobody loves donkeys. You know what that is? That's a mule. Yes, sir, it is. Ah, mules are awesome. Mules can't have babies. They don't have the right number of chromosomes because the donkey and the horse are real closely related, but their chromosomes don't quite line up. And so mules can't produce fertile eggs and sperm. They are non-fertile hybrids. They can engage in reproductive behavior. In other words, they can mate, but they can't have babies. No babies will arise from it. And that's what that means. A mule plus a mule equals no offspring whatsoever. So, why on earth, first of all, where do non-fertile hybrids happen? Spoiler alert, they don't happen in the wild. Non-fertile hybrids don't happen in the wild, period. They do happen, we do it on purpose. We breed non-fertile hybrids. Mules are awesome because donkeys are really strong for their size, but they're little. And mules kind of get the best of both. They're big, but they're strong as all get out. So through a lot of American history, when a lot of farming was still done with basically flesh power, if you're a small farmer, draft horses are expensive to feed. Mules, you get a lot of the power of a draft horse. They're strong, but they don't require nearly as much feed. They're cheaper to keep. They basically get better gas mileage. You don't have to raise as much grain for your mules as you would for draft horses. And you can do a lot of the same kind of work because mules are ridiculously strong for their size. They're little powerhouses. There are places where there are zoos where they keep multiple species in contact. They don't separate species. And there have been ligers, which is the lion-tiger hybrid. There have also been people who have intentionally bred lions and tigers to get a liger. Woohoo, it's a novelty animal. It's a terrible idea because it dilutes gene pools. Now, the other one that's interesting, this is why I asked about people who fish. Anybody here ever catch a sawguy? Anybody go walleye fishing? Okay. I, years and years and years ago, worked squeezing walleye for eggs and sperm one very cold spring. Walleye are stocked in many of Ohio's lakes, so the Division of Wildlife pays people about $8 an hour. That's what the grunts like me, I was just out of college, get paid. And you are head to toe in rain gear and rubber boots up to your knees and big like felt gloves. And you're pulling up nets, you're pulling out fish. You stick the fish's nose in your armpit. You hold their tail like this, and you take a cupped hand and you run it along the female's belly, and she will shoot eggs into a bucket. And you just do that all day, all day, all day. You're milking fish. Once you've gotten all the eggs out of her, she goes back overboard. You get one male out of every batch for about every 10 females. Nose in the armpit, hold his tail, tickle his belly. He shoots sperm into the bucket. You put a cap on the bucket. You send it off to the hatchery. More baby walleyes. Well, that's great. Walleyes are a wonderful game fish. They're delicious. They're cool in a lot of ways. Saugers. Has anybody caught a sauger? Anybody know what a sauger? I don't have a picture of a sauger. I'm sorry. It's another game fish species, but they're much smaller. They don't have as much meat on them as a walleye. Walleye get pretty meaty. You can get a lot of good eating off a walleye. Saugers are supposedly really delicious. For people who like the competition aspect of fighting with a fish, apparently saugers, I've never dealt with saugers or sawguys, but saugers are supposed to be like these awesome, game fish. Well, people wanted something that had the fight and the flavor of a sauger, but the size of a walleye. Meet the sawguy. So, Division of Wildlife, the same people I worked for, now what you're doing is you're going to a lake where you have, I've never been on a sawguy boat. So we would pull up, and I worked at Berlin, and we did walleye in Mosquito Lake, big lake. So take the boat out in the middle of Mosquito, there would be a buoy, and down underneath there would be a large set of trap lines and nets, and since I was the new kid on the block and the young one and the grunt, I got to do a lot of the really stinky work. So you haul up the lines, you hook the edge of the net over the side of the boat, you have a long-handled net, you reach in and you have to pull out all those fish and you have to visually identify your walleye, and everything else goes overboard because you've got perch and crappie and bluegill and bass and everything else in there, and you have to very fast identify your walleye, pull those out, milk them. So I'm guessing on a sauger boat, they probably are just pulling the female walleyes, the males go overboard. And I don't know if they have sauger sperm back at the hatchery. I don't know how that works. But anyway, they're fertilizing walleye eggs with sauger sperm, and they're creating these sawguys. They release them into lakes in Ohio. We could look up where, but it's a non-fertile hybrid. Sawguys can't breed more sawguys. They don't have the right chromosomal lineup. If your chromosomes don't line up with the other mate, you don't make a fertile baby. You just have basically eggs that don't get fertilized or get fertilized and immediately are miscarried. Spontaneous abortion. Those are sterile hybrids. It's quite possible that's what happens in the case of mule plus mule. The chromosomes don't line up right, and most cases where chromosomes don't line up right are fatal exceptions. No offspring. Okay. We don't generally see hybrids in the wild because of isolation. So this is actually what we're going to start talking about tomorrow. Is isolation. So species are isolated from one another so that they cannot reproduce together, and this is what leads to the formation of new species. Isolation and disruptive selection are what get you new species out of old species. We will stop there for today.